Okay, exponential growth and decay functions. A nonlinear function in the form of y equals ab to the power of x is an exponential function. What that really means is as x increases by a constant amount, y will change by a constant factor. In other words, as you're adding a constant amount to x, y is being multiplied by a constant amount. You'll notice there are also some restrictions on a. A can't be 0, otherwise you get y equals 0, which is linear. B can't be 1, otherwise you get y equals a, which is also linear. And then b has to be greater than 0 for it to be an exponential function. Otherwise you get some other weird looking stuff. Exponential growth, when the exponential function is y equals ab to the power of x, and it increases by an amount greater than 1. In other words, b becomes greater than 1. We call that a growth factor. Okay, b is our growth factor when it's greater than 1. If b is less than 1, we call it less than 1 but greater than 0. We call that a decay factor. We call that exponential decay. So, for instance, if you had y equals a times, actually, let's give it a number. Let's just say a is 3, or you know what? Let's say a is 1. Okay, a times b, which we'll say is 2. To the x. That is a growth function because of the 2. It's greater than 1. Whereas, and our growth factor is 2 there. Whereas y equals 1 times, say, 1/2, which we'll put in parentheses to the power of x. That's a decay function because 1/2 is between 0 and 1. And then an asymptote is a line that a graph approaches but does not meet. The asymptote for this graph right here is actually the y-axis, or excuse me, the x-axis. That would be our asymptote. Or rather than saying x-axis, we could also say where y equals 0. So the asymptote for this graph is y equals 0. All right. One of these graphing exponential growth and decay functions. To graph an exponential function and form y equals abx, first find the y-intercept. The y-intercept, just like with any graph, is when x equals 0. And then we'll create a table of values that includes two values greater than or less than the y-intercept. All right, so tell whether this represents growth or decay and then graph. So first I look at it. I look at the 2. That's our b term. If you think of y equals ab to the x. B is 2, it's greater than 1, therefore this is growth. All right. Our y-intercept is when x is 0, so I'm going to go ahead and put my rule in 3 times 2 to the power of x. When x is 0, so 3 times 2 to the 0, our y-intercept is just 3 times 2 to the 0 is 1, so it's 3. Y-intercept is 3. You'll notice your a term is also 3. Okay, your a term is always going to be your y-intercept when you're dealing with these. All right, so that's another way to identify the y-intercept. Then I'm going to go ahead and use 1 and 2, -1 and -2, just two values above and below, or before and after the y-intercept. So 3 times 2 to the first, 3 times 2 to the second. So notice I'm just substituting values in for x here. 3 times 2 to the -1st. Oh. And then 3 times 2 to the -2nd. Okay, well, 3 times 2 to the -2nd, 2 to the -2nd is 1 over 2 to the 2nd. Or 1 over 4, so this is 3/4. Okay, the other way to think about it, 0.75 may make a little more sense on your graph. Okay, -1, that's 3 times 1 over 2, the 3/2, which may make sense to see that as 1.5. 3 times 2 to the first, 3 times 2 are 6, and 3 times 2 to the second is 3 times 9, which is 18. Okay? No, I'm sorry, that's not 3 times 9, that's 3 times 4. That changes that, that's 12. Okay, by the way I was just doing quick checks in my head, make sure I did my math right. Note my rate of growth is 2. Okay, so since my rate is 2, that means I'm doubling every time. I'm multiplying it by every time. That's my b term. And so that's how I when I said, oh, it's 18, and then I was like, that doesn't make sense, it's 2. I have to be doubling every time. So 1.5 times 2 is 3. 0.75 times 2 is 1.5. So that's how that B term is seen in our table. Okay, so I graph those. Negative 2 3/4, and then negative 1 1/2, and then 3/2, or 0.3, excuse me, and 1/6, and 2/12. Okay. All right. So there we got it. That's my growth function. And my domain, well, domain is my x values. It's going to the left and to the right forever on my graph. It's always going this way. It's always going that way. So it's all real numbers. My range, it won't ever get bigger or cross the x-axis, or excuse me, the y. Yeah, it will never cross the x-axis. It gets infinitely close to the x-axis. Notice we just keep cutting in half. Never actually get to the x-axis. So it's y is greater than 0. The equation of the x-axis is y is 0. So it approaches that asymptote. Remember that asymptote we just talked about? At y equals 0. Okay, so range is y is greater than 0. Okay, let's try another one. This one we're looking at it, same information up above here. So we're identifying if it's growth or decay and then graphing. My B term this time is 1/2. That means this is decay. It also means in my, oh, I better spell decay right. It also means in my table I'm cutting in half every time. My A term, which is the y-intercept, is 3. Okay, and so if I'm going to go ahead and put 0 there, 3 times 1/2 to the 0, that's 3. 3 times 1/2 to the first, that's 3 times 1/2 to the first, or 3/2, also known as 1.5. 2, 3 times 1/2 to the second, which is 3 times 1/4, which is 0.75. And then negative 1, 3 times 1/2 to the negative first. Put parentheses there as we substituted. That is 3 times 1 or 2/1, which is 6. And then negative 2, 3 times 1/2 to the negative second. Remember, if you're raising a fraction to a negative exponent, all you're doing is taking the reciprocal of that fraction. Okay, so this becomes 3 times 2 to the second, which is 4, or 12. The other way to think about it, remember, I've got to cut in half every time. There's my multiplying by 1/2. Or if you're going or if you think of it this way, you're going opposite of what we were just doing. Okay. So my graph here is I now have negative 2, 12, negative 1, 6, 0, 3, 1, 1.5, and 2, 3/4, and we could keep going, you know. So you can kind of see the pattern there. You just continue to cut in half, and there we've got it. My domain, once again, all real numbers. My range is y is still greater than 0 because that asymptote is at y equals 0. Okay, this is a decay function. All right, well, let's move past that. Let's talk about some other info here. Exponential growth model is when the function y equals abx increases by a constant factor greater than 1. We talked about that. But we're going to go ahead and break up that b term now to look like this. We're going to explore that b a little more. So we're going to always start at 100% here, because the 1 represents 100% of the original. So if you have money, it represents all of your money that you've invested. Okay, if you're talking about a substance, it represents 100% of your substance. Okay, and that's the same in growth or decay. In decay, we are taking 100% and we are subtracting an amount. Whereas in growth, we're taking 100% and we are adding an amount. So we've got the addition and subtraction piece. Okay, so we're either increasing from 100% or 1, or we're decreasing from 100% or 1. When we decrease, it's decay. When we increase, it's growth. Okay. So let's look at some problems with that. Using the population, or using an exponential growth and decay model, the population of a city grows at a rate of 5% per year. The population in year 2010 was 400,000. Write an exponential growth or function that represents the population t years after 2010. Well, the first thing we need to do is look at our function. Y equals a times b, which we're saying is 1 plus or minus r to the t. Now I put plus or minus r to the t because we could either have one or the other depending upon if we're dealing with growth or decay. It's going to be one or the other. Okay? Whoa, let's go back to that there. All right. The other things we want to note is A is we know it's our y-intercept, but it's also our initial amount, or your beginning amount, the amount you start with, the 100%. The 1 represents 100% of original. Okay. The plus or minus, remember it's plus, is growth. And minus is decay. And then R is the percent of change in decimal form. Okay? And then T, time in years. All right, I didn't give myself tons of room there, but hopefully that helps out. All right, so we look at this, I look at this and I look at that, and there's my percent change. 5% is the same thing as 0.05. So when you think of percent, think of cents, like 5 cents. Okay, 0.05. My initial amount, so this, by the way, is R. My initial amount is A. Okay, 400,000. So if I'm going ahead and writing this, they already tell me it's t years, so I'm going to leave that in. So I'm going to have y equals a times 1 plus r, because I am increasing, I am growing, to the power of t. So that's y equals 400,000 times 1 plus my rate of 0.05 to the power of t. Now you'll notice when I simplify the parentheses here, I get 1.05. And remember our original form of y equals ab to the x? Well, here's a, here's b, here's x. We just changed x to t. Time is usually always your independent variable x. Okay? And so really we haven't switched anything around other than we've explored our b term. We've decided we're going to really look at the rate. The rate is either going up or down based upon a percent. We're identifying if it's going up or down with the plus and minus, and then the percent is our decimal form there. Okay? So what will the population, by the way, this is what they're asking for. What will the population be in 2020? Well, if we use our model or our equation there, think of, they said after 2010. That's a key statement there. I guess I should box that whole thing. So that means time starts in 2010. So 2020 minus the start of time, according to this problem, 2010 is 10. That is t. Okay, which we are going to make 10. So we do our math there. We're actually going to get an approximate value. Let's go ahead and round to the nearest person there. Let's change this up here. You get 651,558. Approximately that. All right. Very good. Let's try another one. Let's look at a different situation. Your new computer, $900 computer depreciates. It means it goes down. You could think of depreciate as decreases. Appreciate, by the way, is increases by 23%. Hey, there's our percent. Our R value is 0.23 as a decimal per year. 900 is our A value. Okay, so if I use the form y equals A times 1 plus or minus B, and I'm going to go minus B this time, to the power of t. Write an exponential function that represents the value after t years. Well, that's just y equals 900 times 1 minus 0.23 to the power of t, which is, when we simplify, y equals 900. Notice my b term now is less than 1 when I do the math there. Okay, there's my decay. So it's decaying there. What will it be worth in 7 years? Well, that's when we substitute 7 in for t. So 900 times 0.07, or excuse me, 0.77 to the power of 7. That's a lot of 7. Okay, substitute that 7 in. And if we go to the nearest cent, your value would be, let's see, $144.44. A lot of fours now. When will your computer be worth $100? Use a calculator. Okay, so I'm going to go ahead and show that. I'm going to have to pause to get a program here. So what we know is the value of the computer is y. So we're going to have 100, it's our y value, is equal to 900 times 0.77. Sorry, I'm writing vertically on my screen. To the power of t. Okay? And so since we're trying to solve for t and we haven't talked about logarithms, which is how you usually solve that, what I'm going to do is I'm going to use a system. I'm going to say this side is a y value. So y equals 100. And this side is also going to be a y value. So I'm breaking this up into two different equations. Y equals 900 times 0.77 to the power of t. Or x, you know, they mean the same thing. Okay, and so I'm going to use Desmos. So let me get to that. So I have y equals 100. And I have y equals 900 times 0.77 to the power of, and I'm going to call it x. I know it's t, but there we go. You notice nothing showed up on my graph because I have y equals 100, so I really have to zoom out. Hey, there's a piece. And what I'm looking for is when these two lines intersect. And it looks like it's right there. So when x is 8.4, y is 100. So 8.4. So the answer would be, when will the value of the computer be worth 100? Well, after about 8.4 years. All right, they don't tell us what year we started there, so that's how we got it. All right. Well, let's go ahead and move on to a different concept here. Rewriting an exponential function. To rewrite an exponential function to determine the rate of exponential growth or decay, and then to define the decay factor, you have to think of the form of y equals ab to the x again. And once again, when we're looking at this, x has to be it has to be a 1x up here. It can't be 1/2 x or 1/4 x or x plus 3. It has to just be x. So when I look at both of these equations that they give us, the problem is in this one, it's x over 2, and in this one, it's x minus 4. So it has to just be x. So that's something to recognize right away. So the way we deal with this is we have to think of our properties of exponents. So if you think back to how you deal with properties of exponents, how do you get x divided by 2? When I divide by something, it's the same thing as multiplying by the reciprocal. So when I divide by 1/2, it's the same as multiplying by 1/2. Or excuse me, when I divide by 2, same as multiplying by 1/2. Okay, and really what does this mean? Well, this means if I were to kind of take this chunk right here and bring it over here, I'm going to have 0.7 to the 1/2 power, all to the power of x. Okay, so I have a power to a power, and I multiply those powers. So really, I now have 90 times, my b term changes to 0.836 repeating, which we'll just call 7, to the power of x. Okay? And so now I have an exponential function, y equals ab to the x. So b is now here. Well, b is my decay or growth factor. In this case, it's a decay factor. Okay, so my decay factor, remember, it's 1 minus. So therefore, I am decaying here, and the decay factor is actually the 0.837. Okay, so a key term there, decay factor, versus the other piece, which is the rate of. So our rate of decay, the rate of decay is our r. So in other words, it's 1 minus 0.837. Okay, and 1 minus 0.837 is 0.163, which in decimal, that's decimal, and in percent is 16.3%. So our rate of decay is 16.3%. All right, so two key terms. Decay factor is before you subtract from 1, how much you went down from 1 is, the decay factor is after you subtract it. So 1 minus that, the actual numeric value. The numeric value of the percent you're going down. It's your actual B term is your decay factor. Okay, so maybe that's a better way to think of it. Your actual B term is your decay factor. Whereas your rate of decay is the amount you're subtracting from 1. Or you're adding from 1 if it's growth. Okay? So two key terms. Note the difference between decay factor and rate of decay. Okay. So let's go ahead and look at this next one. So once again, we want it in y equals abx, and notice I have the x to the 1 or x minus 4 here. And I'm going to go ahead and put a 1 out here to represent my a term. So I have 1 times 1.1 to the x minus 4. And remember, when I'm subtracting, the property I'm dealing with is actually division. So that's where you have, so this is multiply here. So I'm going to have my 1 times, I'm going to actually have 1.1 to the power of x over 1.1 to the power of 4. So same base when I'm dividing, like if I was to simplify this right here, this 1.1 to the x over 1.1 to the 4, it would be this over here. And so that actually is 1 times, and then I'd have, well, 1.1 to the power of 4 is, put the 1.1 to the x there, is 1.464-ish. Okay? And so let's go ahead and take a look at that in a more normal format. I'm going to write it as 1 over 1.464 to the 1.1, or times 1.1 to the x. So now here's my a, and here's my b. Well, just because I don't really like leaving a compound or a decimal in a fraction, I'm going to go ahead and round that to 0.68 when I do the math. Yeah, but my b term never changed, still 1.1 to the x. Okay, so my decay, or excuse me, this one's actually growing. My growth factor is 1.1. Let's say equals 1.1. Okay, my rate of growth is 1.1, or excuse me, is 1 plus r equals 1.1. So in this case, r would have to equal 0.1 or 10%. So my rate of growth is 10%. How much I'm growing from 1. Okay, so hopefully you know the difference between decay, or excuse me, rate of growth and growth factor, and rate of decay and decay factor. I got one piece left, and it's actually called compound interest. And compound interest is, by the way, this would be like a 2-day lesson in a normal class, but compound interest is interest earned on a previously earned interest. So in other words, you put money in a bank, and you earn money on that money for keeping it in the bank, and then the next month you'd earn money upon that money that you'd already earned. So you're continually earning money on the money you invested and the money you've earned. That's compounding. Okay, and it's y equals p times 1 plus r over n to the nt power. P is principal, it's the amount you invest. R is your annual rate. T is your time in years. And n is the number of times the interest is compounded each year. So it's the number of compounding periods. Okay, so I'm going to show you how to kind of deal with this when we're doing a problem. Oops. So I have this formula up here. I've kind of copied it onto this page. And let's go ahead and talk about an actual problem. It's easier to show in this way. You invest $5,000 in an account with 4% annual interest. So in relation to what we've been doing, your principal, it's kind of like your A value, right? So that would be like your A. Okay, y equals A. This would, your 1 plus r over n, that would be like your B. And this would be like your X. Okay. So it's still like a y equals AB to the power of X. But we have a lot more stuff we have to drill down to there. 5,000 is the amount we invest, our principal. 4% is our rate, and we're going to call that 0.04, so it has to be in decimal form. Write a function when 4% is compounded monthly. Okay, so monthly, this is dealing with time, so T here. Okay, monthly is, or excuse me, not T, this is N, the number of times per year. Okay, N, and so monthly is 12 times per year. What will the balance be after 5 years? Well, 5 years represents our T, time in years. Okay, so we have y equals 5,000 times 1 plus 0.04 over 12 to the 12 times 5. So that's y equals, if we do all the math there, okay, let me go ahead and simplify just a little. I'm not going to do any rounding on the inside, so I'm going to leave all the, inside. But I am going to do the 12 times 5, and we're going to call that 60. Okay, so when I actually calculate it out, round to the nearest cent, I'm going to have $6,104.98. All right, that'll be the balance. So in other words, That's my balance. The amount of interest I earned, well, I had $5,000. I earned $1,104.98. That's pretty good. Okay, that's if it's compounded 12 times a year. So I took my rate, I divided it into 12 parts. I got one of those every month, and one of those parts every month, and then I got a total of 60 of them over the course of the time my money was invested. All right, so let's try another one. Let's actually compound it this time. 4% is compounded quarterly. Quarterly means like 4 quarts or 4 quarters in a dollar, so it's 4. All right, so we now have y equals, same balance. We are going now 1 plus 0.04, so notice we're now dividing, rather than by 12, we're dividing by 4. So we get a bigger chunk each time, but we get fewer of those. We get 4 times 5. So that bigger chunk of interest that we will get but we only get it 20 times. We don't get it 60 times. So it compounds less, which means we earn less. Right? So in this case, $6,100.95. That's not a lot less, at least on this investment, but if there's a bigger investment, it could be. It would be a lot less. So that's about a $4 difference there. Okay, write a function when it's compounded semi-annually. Well, semi-annually means twice. Okay, so we have y equals 5,000 times 1 plus 0.04 over 2 to the 2 times 5. So 5,000 times 1 plus 0.04 over 2, so fewer times, or a bigger chunk per year, but fewer times here, 10 times total, which means we will once again make less money. However, we're still making money. It's $6,094.97. Okay. Well, I think that's it. Yep, that's all I got. Good lucky.